Heyo everyone! Let's jump into a new topic, which is that of normal distributions. This will be a brief intro and we will talk more details in additional videos. But a normal distribution is basically just a bell-shaped symmetric distribution. So you know what it looks like. And it is a continuous distribution. If I was to draw this correctly, I would remember to put a vertical axis here with the label of density, but as I mentioned before, sometimes we just don't do that. The horizontal axis should have the name of your variable as usual, and usually that's capital X, or maybe it's capital Y, whatever suits your boat. Also, we mentioned in a previous video that we are using this probability density function as a way to find probability. So you might have some region of interest, maybe like these blue tick marks, from here to here, and the corresponding area would be the probability of observing values between those blue tick marks. So finally, we'll discuss how we actually find those probabilities. But because we're using area as a proxy for probability, the total area must equal a 1. In this new set of topics, we will explore the empirical rule and how we got some of those values. Remember, like the 68, 95, and 99.7% values associated with the empirical rule. We'll kind of validate those finally. What else? This density function is always positive, and that's on the vertical axis, y-axis. Because you can't have negative probability, so you can't have anything getting shaded down here in the orange. That doesn't quite translate. Lastly, the way that these distributions, normal bell-shaped distributions, are defined, they are defined by where is the center, which is, because it's bell-shaped, we use the mean, and how spread out is this distribution about its center. So we also use the dispersion or spread quantity given by standard deviation. So we've got our two best friends, mean and standard deviation. And so those are the baseline qualities that go into a normal bell-shaped distribution. Let's look at an example here just to kind of get our feet wet. The height of calla lilies are normally distributed with mean 30 inches and standard deviation of 2 inches, and that is referring to their height. So we've got some descriptors here about the heights of calla lilies, and we know how they are distributed. And certainly we can write the sentence every time, but we often shorthand this. So for one, I'm going to shorthand our variable. I'll use the letter X today. X is going to represent the heights of these plants. And instead of writing this sentence every time, we often would abbreviate this as x squiggle, the letter n, capital, and in parentheses, the value of the mean, comma, the value of the standard deviation. So this is saying that our random variable x is normally distributed, that's what that n represents, with mean 30 inches and standard deviation 2 inches. So it's a really brief way to get a lot of info about a variable across. Let's draw a probability density function for this variable. Okay, so I've got an axis and I should label it x, or maybe even just height, a little bit more descriptive. And we know that these heights are normally distributed, so I can draw a nice distribution there. I know the mean of these heights is 30 inches. Maybe I should even put inches over here. And just to be a little bit more descriptive with this graph, I'm going to put a couple tick marks that represent a standard deviation away from the mean. And I think that will do it for the side to the right, and we'll go to the left. And a fun fact, the first standard deviation from the mean is supposed to occur at the location in which the normal curve goes from being concave up to concave down. So this would be like you got your cereal bowl and everything's groovy, and here would be like an upside down cereal bowl, not so groovy. There's a little fun fact. I try to draw it reasonably well, but can always use improvement. And from the empirical rule, we know that one standard deviation away from the mean to the left and to the right should encompass about 68% of observations. Again, one more standard deviation to the left and to the right should encompass approximately 95%. And 3 standard deviations below and 3 standard deviations above the mean should encompass most, but not all, of the distribution, 99.7%. And we did this in a previous video, but I still think it's pretty fun to do because we can sort of find the areas in each of these wedges. Because of the symmetry of this function, each of these wedges should be half of 68%. So we know that's 0.34. The next wedge should be, I don't think I'll have space there, 13.5%. The next wedge, even less of a percentage of observations. I believe that's 0.0235. And the very, very end here, maybe I'll use a different color so I don't get mixed up. It's a very small proportion of observations, 0.15%. And because of symmetry, that would also apply on the right side of the distribution. Now, if I asked you a couple questions about this variable, say I wanted to find the probability that x, the random variable for heights, is less than 28 inches, you should be able to determine that using the empirical rule, that is 0.16. Now, what if, though, I asked, what is the probability that our random variable is less than 29 inches? Well, 29 inches, okay, that's not an exact number of standard deviations away from the mean. And so figuring that out without some new tools is going to be kind of challenging. Unless we want to implement calculus, we need a new way to determine these areas, not just at these discrete locations, right? Because this is a continuous variable. We should be able to find probabilities not just at 30, 32, 34, etc., but all throughout the values of this variable. You know, if I did 29.1, I should be able to figure that out. And so that's what we're going to talk about in the next video, next video, when we will talk about standardization. And we will see where we got these empirical rule values. We'll validate them, and we'll be able to find probabilities for any normally distributed variable. See you there.